In this example, we are going to find all solutions for the equation 2 times cosine squared of x plus square root of 2 times cosine of x is equal to 0. We are going to keep all our answers exact. So in this case, we have multiple pieces here. We have multiple terms that are involving trigonometric functions. So some may look at this and find this to be a little bit overly complex, and I might agree with that because trigonometric functions just physically take up a lot of space. So what we can do, if you would like, you don't need to do this, but if you want to simplify this, we can, for the time being, substitute cosine of x with another variable just to make this look a little bit cleaner. I will, in this case, replace cosine of x, let's say, with the variable a. If I do that, then I can rewrite my original equation of 2 cosine squared x plus square root of 2 cosine x instead as 2a squared plus the square root of 2 times a is equal to 0. Now this looks a little bit cleaner to me. It's a little bit simpler because there's less going on really. My goal right now to get a by itself, and I'll replace that again with cosine of x in a moment. But here, since I see two terms and they both have that value of a, I should be able to factor out a here and get a times the remainder, which would be 2a plus the square root of 2 is equal to 0. Now at this point, note that we have something times another thing, so we have two terms multiplied that equal specifically 0. When you have two things multiplied to equal 0, that means that one of those two terms must equal 0. This is only true, this is only a fact that you can use when you have two things multiplied that equal 0, not any other number. So if this were to equal 4, I can't say that one term would equal 2 and the other term could equal 2. Because maybe one term equals 4, the other one equals 1. Or maybe one of the terms equals 1/8 and the other term equals 32. There's a lot of different combinations for that. However, with 0, we know that one of these two terms would equal 0. So we can set them equal to 0. I could say a equals 0 would be a solution for this, as well as 2a plus the square root of 2 would equal 0 is another possibility. That second possibility, I'm going to maneuver a little bit to get a by itself there. We can subtract square root of 2 and divide by 2 to get a equals negative, when we subtracted the square root of 2, divided by 2. Now remember, at this point, our goal was not to solve for a. A was just a substitute, was just a variable I used for the time being to make it look easier for me. Now we should replace a again with cosine of x. To remember what our original goal here is. Cosine of x is equal to 0. And also cosine of x is equal to negative square root of 2 over 2. So now we're trying to find any solution that would hold for this. Any cases where cosine of x equals 0 and cosine of x equals negative square root of 2 over 2. Those two values are pretty convenient actually, because both 0 and negative square root of 2 over 2 are values defined well in the unit circle. So when I would try to use an inverse cosine function to get x by itself here, for the first set of values, if I use inverse cosine, I don't need to keep my solution sets with arc cosine because I should know where cosine equals 0. Well, that happens at a couple places. That would happen at pi halves radians, and it would also happen at 3 pi halves radians. Keep in mind that the original question, though, was to find all solutions, so not just the ones within the unit circle. So we would want to consider any coterminal angle measures for these as well. And we can simplify that, and I will do so in a moment. But first, let's address the second set of solutions, where cosine of x is equal to negative square root of 2 over 2. Again, when I apply an inverse cosine function in order to get x by itself, I should not need to keep it as arc cosine of negative square root of 2 over 2, because I should know where cosine equals negative square root of 2 over 2. Within the unit circle, cosine equals square root of 2 over 2 at multiples of pi over 4, and it happens to be negative in quadrant 2 and 3 for cosine. So that would be in quadrant 2, that'd be 3 pi over 4. And in quadrant 3, that would be 5 pi over 4. Note that if you use the traditional set of values for the infinite solution set for arc cosine, you would get 3 pi over 4 and possibly negative 3 pi over 4. But that would mean the same thing here. Still, though, we need the full infinite solution set, so also plus 2 pi k on each of these solutions. Now from here, I have my final answer. So I have my final answer of solutions. I have 3 pi over 4 plus 2 pi k. In all cases here, k is going to be an integer. We have 5 pi over 4 plus 2 pi k. And the first two solutions there, pi halves plus 2 pi k and 3 pi halves plus 2 pi k, if you would like, you should be able to simplify that, because I can write these two expressions as just one line, as just pi halves plus, instead of 2 pi k, just pi k. Pi halves plus pi k will generate all the coterminal angle measures of pi halves, as well as 3 pi halves and their coterminal angle measures. So that would be my final set of solutions. Keep in mind, when you are done, you should also be able to check your work by taking any of our answers here and plugging it back into the original equation to make sure the equivalence is valid.